Hello and welcome to section 2.6 related rates, and in this unit, in this section, we're going to go through and deal with problems where we need to solve how something is changing over time. And so when we were doing in the last section, when we were doing implicit differentiation, we were always doing with respect to x, but now we're going to differentiate with respect to time. And so that doesn't really change much, except for we have to understand that y is respect to time and x has respect to time. So as it changes, when we differentiate, these guys are functions with respect to time, y is, so I have to add on my chain rule, which would be like a dy dt, and so on for the next one. So a good thing to do is to kind of go through and write down what we know. Well, we know the equation is y equals x squared plus 3. We also know that dx, the change in x with respect to time, is 2 when x equals 1. Now, what we're really trying to do is we are trying to find dy dt when x, well, let me just do this here, when x is 1. Okay, and so I'm going to move this x equals 1 over here because this is the specific case. X equaling 1 is my specific case. So what I'm going to do is I'm going to differentiate this function as if it was any other function out there. And then I'm going to go through and plug in my specific case and find out what's happening. And you'll see this is kind of a common theme through all these problems. These are difficult problems because they're word problems, and you will see this as we go along. So when I do this, I'm going to go through and say, okay, I've got the equation y equals x squared plus 3, and when I differentiate y goes to 1, so I get dy dt. I have to keep track that y was a function with respect to t. X will turn into x squared will turn into 2x, but x is also a function with respect to t, so I get this dx dt, and 3 is a constant, so it becomes 0. So this is my change in y function with respect to time and my change in x function with respect to time. So now I go through and use my specific information that dx dt is 2 when x is 1. So if I want to find dy dt in this specific case, I'm going to go through and say, oh, well, now I can plug in my specifics, which is x is 1 and dx dt is 2. And so when I simplify this out, I end up with dy dt equaling 4. So this could be, meters per second. This could be anything on how a y would change. So this is the same thing that we did before, that the equation, this is just my know part that we were talking about. And so this was, I knew this equation, I was given this rate, this is specific to the question itself, and we know we're trying to find dy dt when x is 1. So after differentiation, we're going to plug these guys in. So you have to remember that you have to look for the specific because that's where we plug in the information. So our guidelines for this is to figure out what we know, figure out what we don't know, sketch any pictures or anything like that. Then we would go ahead and write an equation involving the variables whose rates change, either are given or to be determined. So we do that, and then we use the chain rule, implicit differentiation, whatever it takes to differentiate with respect to time. And then after that we'll substitute. So you'll notice that this last one was substituting in the specific case. So I don't know how many years I've been doing this, but as many years as I've been doing this, kids always want to plug in the numbers too early, and it ends up causing all kinds of havoc on these problems. So remember that it's the specific case you're looking for, and you want to save that to the end. Alright, so we have this example here where we have a pond where we're dropped a pebble in, and the radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? So we need to remember our geometry and figure out what we know. Well, we know in this case that we are getting the change in the outer ripple is increasing at a constant rate of 1 foot per second. Okay, 1 foot per second is a key that this is a rate of change. So that means that dr dt is 1 foot per second. Okay, that's a rate. When the radius is 4, at what rate is the total area changing? So we need to find, in this case, dA dt. How is the area changing when the radius is 4? There's my specific case. So the question is, the one thing we don't know is, what equation are we going to use? What equation are we going to differentiate around? Well, the question is about the total area. And total area of what? Well, these are circles. So I got to remember my geometry. That area is pi r squared. So now, to solve this problem, I have to find dA dt when the radius is 4 and dr dt is 1 foot per second. So now I'm going to go ahead and differentiate the area equation. And when I differentiate the area equation, I get dA dt will equal pi times 2r, and don't forget that r is with respect to time, so dr dt. Radius is changing with respect to time. So now that I've differentiated, this is general. I could plug in any rate here and any radius and find out how the area is changing depending on the given information. Now it's time to plug in what the specific cases are, that the radius is 4 when dr dt is 1. So to find dA dt, I will say, okay, well, it's 2 pi, my radius is 4, and dr dt happens to be 1 foot per second. So now this is foot seconds, radius is foot. So you'll notice that when I'm multiplying these guys together, dA dt will give me 8 pi feet squared per second. And now that should make sense that my area is changing. So by using my units that I have here, that one is a foot second and one is feet, is my radius, 4 feet. And so then when I multiply those guys together, I get feet squared per second. So that would mean that's how my area is changing over time. And so then my final example for this is for today, and like I said, we're going to practice this stuff a lot in class. So the air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Okay, cubic feet is a good thing to know, that this is cubic, so that's feet cubed. And whenever we have the measurement cubed, we're dealing with volume. So we're going to have to deal with a volume of a spherical balloon, and we want to find the rate of change of the radius when the radius is 2 feet. So we need to find dr dt, that's our specific, when the radius is 2. So we have to think of, we need to know the volume equation for a sphere, and we need to know, we need to know how this is going to change. Well, we know, if you look at this, that they told us 4.5 cubic feet per minute. Well, what is that? That is a volume changing. So dV dt is 4.5 feet cubed per minute. So that's another thing that we know. So how are we going to deal with this? Well, we need to remember the volume of a sphere, and the volume of a sphere equation from geometry again is 4/3 pi r cubed. So now that I have my volume equation, these guys are my specifics to what's going on here. So I need to differentiate the volume equation. And so that would give me dV dt equals 4/3 times pi times 3r, r squared dr dt. Well, if that's the case, then I can kind of simplify this and get dV dt equals 4 pi r squared dr dt. Now I've differentiated this volume, and now I'm going to plug in what I know. Well, I know the radius is 2. I know the change in volume is 4.5, so I'm going to plug those guys into my problem and get 4.5 equals 4 pi times the radius 2 squared dr dt. Now it's just an algebra problem for me to solve for dr dt. So I'm going to divide, this is 16 pi, so it's going to be 4.5 over 16 pi will equal dr dt. Well, if I want to calculate that out, I could go ahead and figure that out, and that's going to be approximately 0.09 feet per minute. And so you should understand that this guy right here was feet cubed per minute, and then this guy is feet, and it becomes feet squared, so this is feet squared, and this guy is feet cubed per minute. So the squared and the cubed cancel out, so that's how I end up with that unit of measurement for my answer. So again, we will practice this in class. Please come prepared with your questions, and we will talk more about this and have plenty of time to practice this. So thank you.